Here's the definition of distance. The distance between two objects is the length of the shortest path joining them. That definition leads to this postulate. A line segment is the shortest path between 2 points. Or perhaps you've heard the sentence, the shortest distance between 2 points is a straight line. Another definition, equidistant. If 2 points A and B are the same distance from a third point C, then point C is said to be equidistant from points A and B. Another way to state that is as follows. If segment AC is congruent to segment BC, then point C is said to be equidistant from points A and B. And here's a picture. We have point C, and we have a segment from point C to both points A and B, and we've marked those two segments as congruent. And that brings us to the equidistant theorem. If 2 points are each equidistant from the endpoints of a segment, then the 2 points determine the perpendicular bisector of that segment. And the proof of this theorem was given in the previous lesson shown here. If you'd like to study it further, I recommend you stop the video. This proves it for the case where 1 point is above the line and 1 point is below the line, and the 2 points are Z and X. It can also be proven if both of the points are on the same side of the line, in this case both above the line. Because we've kept the labeling the same, the proof is identical. The triangles don't look quite the same. In our detour proof, there's the first pair of triangles that we prove congruent. Those two triangles look a lot different than the two in our first case. And there's the second pair of triangles we prove congruent. One difference in our second case, though, you'll notice we have line ZX in the proof and also in step 12 because segment ZX doesn't actually intersect with our segment YW. So while segment ZX helps determine our line ZX, the segment itself is not the perpendicular bisector. But the line that the segment is contained in, line ZX, is the perpendicular bisector of YW. And the third case is if one of our 2 points lies on YW. And of course, if it's equidistant from Y and W, then it has to be the midpoint of YW. And then the proof is much simpler. We do not need a detour proof. We just need to show that angles YXZ and angle WXZ are congruent, and since they form a linear pair, they're congruent and they're right angles, and therefore ZX is the perpendicular bisector of YW. So we've proved it for 3 cases. Case 1, where 1 point was on one side of the segment and the other point was on the other side. Case 2, where both points were on the same side of the segment. And this case, case number 3, where one of the points lies on the segment. And here's a theorem very closely related to the equidistant theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment. Well, let's set up and look at that proof. The two givens combined tell us that ZV is the perpendicular bisector of YW. And then we use those givens to mark what they tell us, as shown, that the XY is congruent to XW, and that the perpendicular lines form right angles. And then we start with our statements. We state the first given, and then we state the second given. And we know those two angles are right angles because perpendicular lines form right angles. For reason number 3, you could also write definition of perpendicular lines. Step 4 is we state that those two angles are congruent because all right angles are congruent. And in step 5, XU is congruent to itself. I hope you all remember by now that that's the reflexive property. Now we've got a pair of triangles congruent by side angle side. And because that pair of triangles is congruent, we now know that YU is congruent to WU by corresponding parts of congruent triangles congruent, and therefore we've proven this theorem. Well, our 2 theorems have made a lot of things go a lot faster, and one example is shown here. We're given this diagram, and we're given that angle 1 and angle 2 are congruent, and angles 3 and 4 are congruent. And if we're trying to prove that ZX is the perpendicular bisector of YW, before we had proven the equidistant theorem, we would have started like this. We would have proved these 2 pairs of segments congruent by if sides then angles. Then we would have proven the two green triangles congruent by side, 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 because the shared side, z-axis, is congruent to itself. And then we would have used corresponding parts to prove the two angles at the top congruent, and then angle, side, angle to prove the two blue triangles congruent, which is a detour proof. And from there, we'd know that YW is congruent to UW by corresponding parts, and also by corresponding parts that angles ZWU and ZWY are congruent, and they have to be right angles, because if congruent angles form a linear pair, they are right angles. And from all of that, we are able to state that ZX is the perpendicular bisector of YU. But now that we've proven the equidistant theorem, we can start with this given, use the given pairs of congruent angles to show these segments are congruent, and once we've shown these segments are congruent, and then we can apply our equidistant theorem to prove that ZX is the perpendicular bisector of YU. We've saved a lot of steps now that we know and have proven the equidistant theorem. In this lesson, we looked at the definition of distance. The distance between two objects is the length of the shortest path joining them, and a postulate that comes from that definition: a line segment is the shortest path between 2 points. We also looked at the definition of equidistant. If 2 points A and B are the same distance from a third point C, then C is said to be equidistant from points A and B. And then the equidistant theorem. If 2 points are each equidistant from the endpoints of a segment, then the 2 points determine the perpendicular bisector of that segment. And finally, a related theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment.